So, hi everyone, thank you for being here. So, I'm Marc Teyssier, and today I will present you MobiLimb, a project about augmenting mobile devices with a robotic limb. So, this project has been made with Gilles, Catherine Pelachaud, and Eric Lecolinet at Télécom Paris and Sorbonne Université, France. First, what is MobiLimb? So MobiLimb is a robotic limb inspired by a robotic finger that can be plugged to a mobile device. So in this presentation, I will show you that augmenting mobile devices with a robotic arm can improve the input and output modalities of the smartphone. And I will show you application of how it can be used as a tool, as a partner, or as a medium. And finally, in this presentation, I will discuss the opportunities of extending existing devices with robotic actuators. So first, I want to start by talking about mobile devices in general. So as you may know, mobile devices are the object we use most of the time. So almost everybody has access to a mobile device, and we are in constant interaction with them several hours a day. But why we use it so much? Well, it might be because it's becoming the main tool for mediated communication, right? We interact with it by talking, by reading, sending text messages, typing on the screen, so it's also maintaining the connection between the people, between the real people. It might also be because we are developing an emotional link with the object mobile device itself. So when we look at it, we smile. Alone, it's becoming like a comfort object. We touch it like a companion or a friend. So, however, the mobile devices are still inert. They are motionless and they are not alive at all. So the fact of not being alive, if we translate it in SIGCHI terms, it means that they have limited input and output modalities. But why should we improve the input and output modalities of this device? Well, we think it's an opportunity to improve the global user experience with these devices, to enhance the communication between people, and also to explore new modalities and senses. So, considering all of that, we ask ourselves, how can we overcome the limitation of a mobile device? So, hopefully in SIGCHI, creating new interaction for mobile devices have been largely explored. So we were lucky, especially recently. The work around shape-changing interfaces allow to change the form factor of the phone itself, so they can provide rich haptic feedback and display information, like here, haptic edge display. They also can allow movement of the phone itself and might perform some lifelike animation, like almost organic animation. However, the amplitude of the actuation is somehow limited. So we wanted to go towards a richer actuation and not only consider like output, like here, but also input. So what have been made in SIGCHI toward this direction? We think that robotic might be a good approach because robotic interfaces for SIGCHI allow both input and output with a large amplitude. So the interfaces can have a radical form factor, like here they're used to augment existing interfaces with tangible manipulation in chain form, but then they can also be used to augment the human by adding additional robotic finger or members, like here the project by Song or the project we're going to see in the next station after me. So all of that is not only possible because robotic is now easy to do and it's cheap, but it is also a real emerging trend in SIGCHI to go towards more physical interfaces and actuated interfaces. So more generally, augmenting existing input devices with robotic actuation have also been explored, like the moving computer mouse or keyboard, for instance, here. So based on all this work, we developed MobiLimb. So the development of MobiLimb was motivated by three goals. We first want to use the robotic to augment the mobile devices, because robotics are allowed to change radically and quickly the shape of the device with only few motors. It is also one of our goals to make it reproducible easily. Then we also want to develop meaningful interaction by having an interface that goes beyond the screen in the physical world. And finally, like it's obvious, but we want to explore the perception of a limb attached to a phone. Like, how does it feel? How do people react? That's actually what motivated the choice factor of MobiLimb. So, as I told you, MobiLimb is an extension that can be plugged to any smartphone, and that works right away. So, MobiLimb is capable of, first, outputs. because the combination of the motors inside can display, MobiLimb can display physical elements in addition with the visual information provided by the screen. So also the external appearance here can be changed to have different look and feel. Like for instance here it's black, but I'm going to show you in this presentation different. So MobiLimb is also capable of inputs. So the device can be manipulated and its rotation is detected by the application. So also by adding sensors at the surface of the device, it's also possible to detect touch on the surface. And finally, the device is modular. So it can be plugged to other devices and the extremity can be switched with other components. It can serve to improve ergonomy by maintaining like static form factor or even interact with the surrounding environment. So now that I talked briefly about what it's capable of, let's talk about the possible use cases of this device. We foresee three main use cases categories. So MobiLimb as a tool, as a partner, and as a medium. So I'm going to explain that a little bit in detail, starting by MobiLimb as a tool. So MobiLimb offers tangible affordances and expressive control with the goal of assisting the user interaction. If today we want to manipulate a 3D object on a smartphone, for instance, it's difficult to do only with like, the capacitive screen. As a motor, the motors allow manipulation. We propose here to use MobiLimb as an augmented joystick. The user moves the device to rig a virtual character. There is a one-to-one mapping between the rotation of the device and the articulation of the character, like the limb. So it leads to a more engaging experience. It can also use the internal sensors of the phone. By using, for instance, data and location, it can orient a light output in the proper direction. But what if we replace this light by a camera? Like our interface could be used to perform active visual tracking. So, yeah. All these projects, those two projects depend like, on a direct interaction by the user. But it can also have predetermined behavior and act as a partner in collaboration with the user to foster curiosity and engagement. Some smartphone applications now have virtual avatars, and they are usually displayed on the screen of the device only. But the physical augmentation can improve their expressive qualities and communicate different emotions through movements, like this cat and its moving tail. So you can notice here that the texture of the device has changed to look like animal fur, to reinforce the link with the avatar and the physical, tangible object. So the visual appearance can also change by changing the extremity of the device. Here, it's replaced with a static element to resemble like a scorpion tail. So all this avatar and autonomous behavior are usually controlled by the phone or an artificial intelligence on the phone. But MobiLimb can also be triggered at distance by a remote partner. So it's going to act as a medium between two people. So let's take like today, for instance, how we communicate through the phone. Well, there is voice and text, but the haptic feedback is not that explored. But during real-life communication, we communicate through touch. We touch people, and we use this modality. So with a robotic extension like that, we can provide kinesthetic feedback by touching the user on the wrist or the back of the hand, for instance. It can send a remote stroke to comfort a friend or other things like that. And if we are in a situation where we can't touch the user, it can directly interact with the surfaces and the environment. By adding just a pen at its extremity, it breaks kind of the wall of the virtual content and goes in the physical world to write a message, for instance, sent from a remote friend. So here I just showcase a few examples, but all the scenarios here are explored with the same device. So the different use cases here are not only for MobiLimb, but can be extended to other devices augmented with robotic actuation. Now, how is it made? What I would like to show you here is that it's easy to build and reproduce, and its implementation is modular. It's easy to use because the device is very simple in its design. So it's composed of 5 chained servo motors. So why 5? Well, because it was a good compromise between the degrees of freedom and the power consumption. So the motors are controlled by an Arduino board. Everything is enclosed in a 3D printed shell that lies behind the phone. And it's connected to the phone with a micro USB controller, which is like usual. And the tip of the device, as I told you, is modular. We actually developed extremity with electronic components which can be used to detect inputs, like touch or proximity, or outputs, like LEDs, or more like static shells, as I show you, to change the appearance of the device. So about the MobiLimb system, it's composed of two main parts. Obviously the hardware, which is connected to an Android application, so the software. On the hardware side, the motors are connected to an off-the-shelf Arduino Leonardo. So the Arduino is using the micro USB port to get its power and share the data with the application. And for the software, we built a high-level API in Unity that allows to control the motors and which is used also as a rendering engine. So what was important for this project is the scenarios and all the possible interactions that a designer can develop. So for the designers, especially, we implemented a physical simulation layer, providing 3 ways to control the device easily. First, using keyframe animations, like traditional animation in forward kinematics, the designer can animate step by step, and it's played back by the device. So it might suffer of a lack of naturalness, so we added the possibility to record and save motion, which can then be played back by the device, so it's more like organic movement. So we can use also this feature to do remote real-time manipulation. And finally, to interact with the environment, the inverse kinematics model allows to follow a specific target and draw, for instance, a square or any shape here. So to sum up this part, like from the fabrication to simulation, a robotic approach is easy to do and not expensive for both the hardware and the software. The total cost of the device is around $20, $25, which is quite cheap. So of course there are some limitations, especially the torque of the motor might be like too low, but it's something that the new technology can overcome easily, and like more robust technology. And also, yeah, but however, we think it's a promising approach to use the simple blocks like that. So now to finish a little bit and to open up the possibilities, I would like to discuss a little bit more about the perspective that MobiLimb research proposes and how it can impact future interfaces. So we presented here MobiLimb attached to a smartphone. So it's the smartphone is the object we use, as I told you, most of the time. However, we can wonder how we can use it with other devices. So for that, we explored MobiLimb with a tablet to demonstrate that this approach is actually doable and that we can revisit existing devices by adding those simple actuated interfaces. So a robotic approach like that could be adapted at different scales of devices. So we developed for mobile, phone, and tablet. But what if we built a prototype for smartwatch or desktop? Like what it would look like? We don't know yet, but for smartwatches, we can envision a small object capable of discrete and subtle notification close from the wrist. While if we imagine an interface at a desktop scale, it can be used to touch the user and provide full body haptic feedback or kinesthetic feedback, for instance, in game or in virtual reality. But we don't know what it would look like. We don't know because it will certainly not look like a finger because the scale is different. This aspect was an important part of our work and our initial approach to explore actually the perception of this device when they look like a finger. So by implementing organic movement, the perception of the device changes. It moves, it crawls, and it feels like it's suddenly alive. It's becoming more a life companion. Just with the movement, it can convey emotions. So it might be worth exploring possible interaction with a life companion that becomes phone or companion. We don't know. So we went a little bit further in this direction by working with people specialized in movie special effects to create realistic human skin. So the result here is like an actuated anthropomorphic interface. Yeah. So with a skin layer like that, the perception of the device radically changes, and it feels like it's part human. So these interfaces with organic movement and human-like skin made people react a lot on internet. So how do people react? Well, it's disturbing, this is weird, it's creepy, it's more creepy or it's more creepy. It's like, right, just an example. So, but clearly the object appears as creepy, right? But maybe there is something beyond that has yet to be explored. Like indeed, as humans, we interact with each other by using the human quality. We use a finger, we move, we grab each other, we are made to interact this way. However, people's reaction here suggests that they want a clear distinction between what is an interactive object and what is human. So there is a sociological aspect worth exploring here. I think it's interesting to know why people are not ready to have these animated anthropomorphic interfaces. So yeah, it's creepy, it might be funny, but talking out loud to a device was kind of creepy even like 10 or 15 years ago, but it's not anymore with all the voice interfaces. So considering that, maybe a device that will touch you to convey emotion will not be creepy in 15 years. At least we think that we raised a question, an interesting question for SIGCHI research of what would device look like in the future. Is it a desirable future or not? We don't know yet. So I hope our prototype will inspire you to augment other common interfaces with simple robotic actuation. And I also hope that you will answer the question raised by those anthropomorphic aspects of our device. Thanks for your attention.
Microphones. All right. I'm pretty sure I don't have to pretend that I have questions on this one.
Hi, Daniel Ashbrook, University of Copenhagen. Indeed, creepy, but a lot of fun too. So my question is, are more fingers better? Can I put 2 fingers or 5 or 11 onto my phone, and does that just up everything? Obviously the creep factor, but does it get more useful and more expressive?
So for this prototype, it's just 1 finger, but we could have envisioned different fingers, and we think that the impact it's going to happen, the people are going to be totally different. Like for instance, if we put 5 fingers, it's going to be more like Adam's family thing, but it's going to be different. So 1 finger, it's a good starting point, and it made people react a lot. I think it's.
So in a maybe a little bit more serious direction, then how do you actually measure people's reaction? Like, have you thought about how to think about less in a UIST way and more in a Chi way? How do we talk about how people react to this? How do we think about the utility versus the creepiness and so on?
So we did a user study on the paper. I prepared the slide. See?
Well done.
So we did a user study, just a video-based user study, to know okay, is it a desirable scenario? Do you like it? Is it amusing or is it useful? So we gather some data here. But on the internet, it's we have much more data, and we have to do another study, but which is going to be a more social study, and to explore really why people think that and how they react. So, yeah.
Cool. Very fun. Thanks.
All right. More questions? Come up to the microphone. If not, I'm going to ask one. Go for it.
Oh, thank you. So I'm Shohei Katakura at Meiji University, Japan. So my question, thank you for your interest in your amazing work. So my question is, so your final vision of long vision is more useful for personal or mobile robotics arm, or more artificial things, or just a finger, or more entertainment things?
So that's a good question, because our starting point, we were thinking okay, what is transhumanism? Let's think big. So it's humans that want to be augmented by robots or by devices. And what if we reverse this thinking, and what if the devices themselves wanted to be augmented with human parts? Because human it's great, right? So the vision is more that. So we made a finger, but there might be other possibilities. And just
so mobile augmenting humans devices, right?
Yeah. So yeah, it's devices augmented by human parts. That was the initial thought.
Thank you.
All right. I'd say, Yaman, do you want to start setting up? I'll ask you one more question while Yaman's setting up. I think relates to what Dan Ashbrook was thinking about, which is, it seems that this falls into some uncanny valley, right? Yep. The moment you made it look very anthropomorphic, then into that awkwardness. But what if because you showed some other work where the finger, the extra fingers, was connected somewhere else, right?
Yep.
Do you think that's gonna impact? So it is uncanny because it's attached to my phone, and I go like, why is a human finger attached to a phone? Or sixth finger kind of style things.
Yeah, I think it's uncanny because it's not. We have not seen that before. Mm-hmm. So I think I have to look more into details. But I think our brain, there is something definitely wrong with the feeling of having a mobile device static moving. So yeah, don't remember.
Maybe you just got to rewire the brain. That sounds cool.
Yeah.
All right, one more hand for Marc. He's going to be around, test the device.